Now that we're familiar with the angle pair relationships within our parallel lines and transversals, we're going to now look at how do we go backwards. So instead of being given the parallel lines and looking at the angles, how do we look at angles and lines intersected by a transversal and prove that those lines are parallel? So in order to do that, what we're going to do is we are going to be looking at the converses. So theorems and postulates we're using to prove lines parallel are going to be the converses of what we already know. So you'll see I've printed out the postulates and theorems that we already know. So for example, let's look at the corresponding angles postulate. This should hopefully be very familiar, right? If we have two parallel lines cut by a transversal, then the pairs of corresponding angles are congruent. Okay, so the converse of this postulate is what we can use to prove that the lines are actually parallel. So what we would say here is, okay, so right here, if a pair of corresponding angles are congruent when two lines are cut by a transversal, then the two lines are parallel. So what would we be looking for in your diagram? I'm going to draw it right over here. So if we are given angle 1 is congruent to angle 2, and here's my diagram, right? I have two lines cut by some transversal. Notice how I don't know they're parallel. There's no marks here saying they're parallel. But I know angles 1 and 2 are congruent, then we can conclude, I'll call these lines L and M. We can conclude L is parallel to M. Again, that says conclude. I know that's not very clear. Let me just rewrite that. All right, so again, here we're not given the lines are parallel, but we can show that they are parallel using the converse of what we already know. So you can probably figure out the rest because, again, all we're doing is we're flipping P and Q with all of these theorems. So let's take a look at the alternate interior angles theorem. Okay, so using the converse of the corresponding angles postulate is not the only way to prove lines are parallel. We can also use the converse of the alternate interior angles theorem. So let's go ahead and write that one down. All right, so there it is again. So basically, if you have two lines cut by a transversal and a pair of alternate interior angles are congruent, then we can take that further and say, well, those two lines must have been parallel. So if we bring this to a diagram, again, here, if this is my diagram, call this L, right? Call this M, and again, nowhere am I given in the notation or in the words that L is parallel to M. But I know that angles 1 and 2 are congruent. Since they're in the alternate interior angles position, right, that's the relationship, we can conclude, I really can't write this word today. We can conclude that L is parallel to M, okay? So this is basically the theme of today's notes. So let's go ahead and look at the alternate exterior angles theorem and its converse, and the same side interior angles and its converse, and then we'll look at a couple examples. Okay, so there they are. So we want to make sure you pause and jot this down. But again, we're looking at the converses, what we have in blue. So the converse of the alternate exterior angles says that if we have a pair of alternate exterior angles that are congruent, then those two lines that are cut by the transversal must be parallel. So if you look over here at this example, right, again, I don't know L and M are parallel from the diagram or from the given information, but I know that these two alternate exterior angles, 1 and 2, are congruent. So then I have enough information to say that L is parallel to M. Okay, finally, same side interior angles. Remember, this is the one that is just a little different because our same side interior angles have to be supplementary. So if you have a pair of same side interior angles that are supplementary, right, that's what you're given or that's what you can use, then our two lines are parallel. So again, our same side interior angles are the only ones that are a little different. We need to make sure they're supplementary. So you can be given that they add up to 180. So therefore, by the definition of supplementary, they're supplementary. And that'll tell us that L is parallel to M. Okay? Let's do a couple examples here, just using our theorems to show that the line L is parallel to to M. So what you need to do here is, obviously, we're using these to prove lines parallel. We want to think about this as a proof, right? What information will help me find out that these two lines are parallel? So I have to go back and use one of those converses. So the very first thing you want to do is identify your angle pair relationships. Remember how we did that on the first day of this chapter? That's what we want to do again. So if I look at angle 1 and angle 5, right? Remember, you can redraw the diagram, highlight, do whatever you want, right? And I see, okay, these two are congruent. Now take a look at those angles. What's the relationship? Well, here, hopefully you're seeing they're in the same position, so they're corresponding angles. Right? So that's what I'm thinking about. So I want to go back and say, well, if they're corresponding angles, can I say that these lines are parallel if my corresponding angles are congruent? And yes, you can. So we can say L is parallel to P by the converse of the corresponding angles postulate. And again, if you don't remember the name, that's fine. You can say the lines are parallel because the corresponding angles are congruent, right? Okay, let's look at part B. This one's got a little more work to go with it. So let me just erase my marks here since we're not looking at 1 and 5 anymore. Okay. Now we're going to look at angle 3 and angle 5. And we're going to use that information when x is 5. Well, remember again, look at the angle pair relationship first. So if it helps, you can do what I'm doing here. I'm going to highlight my angles, angle 3 and angle 5. It doesn't say they're congruent, so I don't want to mark them as congruent. So now looking at these green angles, I want to say, well, what is that angle pair relationship? They're on the same side of the transversal. They're within the two lines, so these are same side interior angles. So again, this is what I'm thinking about in my head. So you can go back and look and say, well, what do I need to know about same side interior angles? And it's right over here. I need to know that they are supplementary. What does supplementary mean? Well, they have to add up to 180, right? So that's what I want to check. Does the measure of angle 3 plus the measure of angle 5 add up to 180? Because that's what's going to tell me if they're supplementary. So let's go ahead and find out. We're going to figure out what happens when x is 5. So substitute in your values. 10 times 5 plus 8, that's going to give me 58 degrees. The measure of angle 5, 25 times 5 minus 3, so that's going to give me 122 degrees. So what happens when I add measure of angle 3 plus measure of angle 5? It's going to be 58 plus 122, which is 180 degrees. So this shows that angle 3 and angle 5 are supplementary. So you want to tell me what, all your work did, right? You don't want to just leave your work and say, yep, they're parallel or whatever, but tell me what that means, right? They equal 1, they add up to 180, therefore they are supplementary. So I can say that L is parallel to P by the converse of the same side interior angles theorem. Please make sure you have that word converse. If you tell me same side interior angles theorem, that's completely different. That tells me the lines are already parallel. You're given the lines that are parallel. So that one word does change the entire theorem. So be wary about that. Again, if you don't want to worry about the vocabulary, you can say, well, L is parallel to P because the same side interior angles are supplementary.